Hello students, welcome to DEY'S Learning. This is an episode of a problem solving series. Today we are going to solve some selected problems on alcohols, phenols and ethers. So let's go. This is our first problem. In the first problem, one epoxide molecule is given, which contains a double bond, and on hydrolysis of this compound will give the major product. Of course, our question is which one will be the major product out of the given four options. So this is our problem. Let us solve it. The solution is given here. My duty is to explain it. Okay, this is our substrate molecule, and in the first step the protonation of the epoxide oxygen occurs, and as a result we get this intermediate, the protonated form of the substrate. And in this intermediate, from this intermediate, two things can be possible. The epoxide ring can be opened in two ways. In the first way, if the ring opens from this side, the carbocation will be formed here, and if the ring opens from this side, the carbocation would be formed here. But of course, this carbocation, this one is definitely more stable than that would occur from the other side, because of course this is a 2-degree carbocation which is more stable. And now the intramolecular nucleophilic attack of the double bond can occur. On the intramolecular nucleophilic attack of the double bond to this carbocation, we get this 5-membered ring compound. This is of course a ring closure reaction. One ring is formed. Now this 5-membered ring is formed, and the carbocation is formed at this position. Look at here. This carbocation is sufficiently stable. Is stable enough because there is alpha carbon, there is another alpha carbon, there is another alpha carbon. So 3 plus 2 plus 2, there is 7 alpha hydrogens are there. So 7 alpha hydrogen will stabilize the carbocation by hyperconjugation. So this is a very stable carbocation. We can think the ring closure can occur from another side, of course, because this ring closure can occur from this side, of course, but then we would get this sort of intermediate, like say like this one. Here carbocation will be formed here, and this is 1, 2, and then oxygen, then OH, this sort of intermediate. But take a close look here. This is a 1-degree carbocation, number 1, and number 2 is a 4-membered ring would be formed, which is very unstable. This system is not stable enough like this one, of course. So this one will be our major product, or major intermediate product. Okay, so let's proceed. Now nucleophilic attack of water molecule can occur and this carbocation, and on attack of water molecule at this carbocation, this protonated form of water molecules containing compound will be formed, and subsequently the deprotonation from here, deprotonation of the oxygen from here, the positively charged oxygen from here, we will get our final product. This is our major product. So this is the solution of the above problem, and we see the problem and the solution in the same screen. So this is our problem and this is our solution, and of course the option B is our correct answer. So let's move to the next problem. So this is our second problem. In this problem, this molecule is given, and with on treatment of this molecule by ethanol in acid medium, in hydrochloric acid medium, will give which one of the following compound? This is our question. And now we need to solve it. The solution is here. Okay, take a close look here. This molecule is given. Now this molecule in the first step, of course, will be protonated, because in hydrochloric acid medium, in acid medium, this double bond and oxygen containing compound must be protonated. And protonation occurs in that way that the resulting carbocation will be stable enough. Of course, this is the criteria. This is the driving force of this reaction. So the carbocation will be formed. Attack of this carbocation to H plus molecule, protonation of this carbon occurs, and as a result the carbocation will be formed at this position. And of course this carbocation is very stable, because the adjacent oxygen atom, which can stabilize the carbocation by its strong pulsar effect, plus resonance effect, plus mesomeric effect. So this carbocation will be formed, and in the next step the ethanol molecule will attack at the carbocation. The nucleophilic attack of the ethanol molecule occur in this step, and as a result we get this type of intermediate. This is the protonated, in which the alcoholic portion, the ethanol portion, is actually protonated, because this oxygen contains 2 lone pair, and here the oxygen contains 1 lone pair, of course. So the oxygen is positively charged, and in the last step the deprotonation, the release of H plus ion occurs from this positively charged oxygen, and as a matter of fact we get this product, and this is our final product, of course. This is actually acetal molecule. This is actually an acetal molecule, which is our product, which is the outcome of the given problem, the product of the given problem. So this is our question, this is our problem, and this is our solution. And of course the option C is the correct answer of the given problem. Next, move to the next problem. This is our third problem. In this problem, this molecule is given, and take a close look here. This is actually an enol ether molecule. One ether bond is here, and this is actually the enol form. This carbon contains 1 double bond in plus ether. So this is actually an enol ether molecule, and on hydrolysis of this compound will form a product. Our question is, which one will be the product of this reaction? These problems are actually very important for exam purposes. There are very subtle differences between the substrates and between the mechanism of the reactions. So very careful for the treatment of these problems. Okay, let's solve the problem. Look at here, in this molecule, in the first step, this molecule will be protonated, the ether oxygen will be protonated, and on protonation of the molecule, we will get this sort of intermediate where the oxygen atom is positively charged. So the nucleophilic attack of water molecule will occur. Nucleophilic attack of the water molecule will occur, and nucleophilic attack of the water molecule will occur here, and as a result the molecule will be fragmented. The molecule will be divided into two parts, and the left portion will form this intermediate, this compound, and the right portion will form the ethanol molecule. So and in the left portion, this is actually an enol, in plus ol, and on tautomerism of this enol form will produce the keto compound. This is your cyclohexanone. So the two final products of this reaction is of course cyclohexanone and the ethanol molecule. So actually the molecule, this bond is actually broken, and this molecule is divided into two parts. This substrate molecule is actually divided into two parts. This portion gives us the cyclohexanone molecule, and this portion actually gives us the ethanol molecule. So ethanol and cyclohexanone is our final product. So this is the solution problem, and this is the solution. This one is the problem, and this one is the solution. And among the given options, of course, option B is our correct choice. Cyclohexanone is the product of the reaction. The side product, the ethanol molecule, is not given in the options. So option B is our correct answer. Let's proceed. This is our problem number 4. This substrate molecule is actually given, and this molecule will be treated by concentrated sulfuric acid and in presence of heat. So the options they given here, we have to solve the problem. Let's go. This is a solution. Take a look here. In the first step, the oxygen atom will be protonated in presence of concentrated sulfuric acid. There will be a lot of protons in the medium. So the keto oxygen will be protonated, and this is our protonated form. And in this protonated form, the oxygen, as a result of protonation, the oxygen atom, the electron withdrawing capacity of the oxygen atom is increased, and as a result it will withdraw electron from here, and of course the electronic pool will be from this side towards oxygen, and this ring expansion, actually when double bond, take a close look here. When this double bond will be shifted, this carbon will be positively polarized, del positive charge will be generated here, and one carbocation will be formed here. And we can think in this way: when this double bond is shifted, the carbocation, the positive charge will be developed here, and as a result the ring expansion occurs. This 5-membered ring, this bond will be broken and this ring expansion occurs, and as a result we get this sort of intermediate. This is a ring expansion process, and in the last step the aromatization occurs. Look at here, due to the shifting of this double bond, the positive charge will be generated here, and after the release of this H plus, after the abstraction of this H plus ion by sulfate molecule, the aromatization occurs. This aromatic ring will be formed, and this is the driving force of this reaction. The stability of the aromatic system is the driving force of this reaction, and this aromatic system will be formed, and this molecule will be our major product. So in the first step, actually three steps occur here. In the first step is the protonation step, the second step is the ring expansion, and the last step, deprotonation, that is the aromatization step, occurs, and subsequently we will get this product. So this is our problem, and this is our problem, and this is our solution, and the correct answer is option A. Is the correct answer of this problem. Okay, let's proceed. So this is our problem number 5. In this problem, this molecule is given. All molecules are very close to one another. Almost all of them, all we have discussed today are actually hydrolysis reactions. So these are actually very important problems for exam purposes. So this molecule is given, and this molecule is treated in acid medium. So the products given looks very disturbing. Very odd looking products, but let's try to solve the problem, and the final product will be found from here. So look at here, in the first step, the protonation of this double bond occurs. Take a look of this molecule. There are many possibilities, because there is one oxygen here, ether oxygen. Here is one hydroxyl group. There is a double bond. So protonation can occur from 3 sides actually. But what will be the outcome? What will be the best possibility to proceed this reaction? Take a close look here. Protonation of this carbon occurs, and as a result this carbocation will be formed, and the carbocation will be formed at the adjacent position of oxygen. So protonation of this carbon occurs, and as a result carbocation is formed here, because this carbocation is stabilized by the Plasser effect of oxygen, by the resonance effect of oxygen, adjacent oxygen atom. This is the resonating structure. So this carbocation will be stable enough. And in the next step, the ring expansion occurs. Because when the adjacent OH group, the oxygen atom of the OH group donates the electron pair over here, this 4-membered ring will be expanded to form the 5-membered one. Because 4-membered ring, there is a ring strain, the internal angle is only 90 degree. So the ring strain is very severe. So ring expansion occurs very easily. And as a result we get this 5-membered ring and adjacent actually spiro compound will be formed. I have denoted the different carbons by the numbers 1, 2, 3, 4. Look at here, actually this carbon becomes the part of the left ring, and as a result this 5-membered ring, the left one, this 5-membered ring is formed. This 5-membered ring will be formed, and in the last step deprotonation occurs, and as a result of deprotonation this is our final product. This product will be formed as the major product. Now we can think about this reaction in another way, of course, because the protonation of this oxygen is of course possible, and as a result of that when this OH group is protonated and after the expulsion of water molecule from here, we would get this carbocation, and this carbocation is very, very unstable. Of course, this carbocation is unstable enough because of the 4-membered ring. Because of the 4-membered ring, the carbocation, the positively charged carbon is actually sp2 hybridized, so its angle should be 120 degree, but the internal angle of the 4-membered ring is only 90 degree, so there is severe angle strain. And you can think this intermediate in another angle, of course. Take a close look. When this double bond will be shifted, the positive charge will be shifted over here, and as a result we get the 4-membered ring with an exocyclic double bond, isn't it? This type of intermediate will be formed, and this resonance stability is actually nothing, because here this exocyclic double bond, again this carbon becomes sp2 hybridized, and this is the exocyclic double bond of a 4-membered ring, so there is no resonance stability. At a first look you can think about this type of resonance stability, but actually this resonance is actually impossible, almost impossible, because this system is very, very, very unstable. Rather than that, this carbocation which is actually formed is much stable than this one. This one is much more stable than this one. Sorry, this one is much more stable than this one. So this carbocation will be formed preferentially, and then the ring expansion occurs, and in the last step deprotonation occurs to give us the final product. So this is our problem. This is our problem number 5, and this is the solution. So the answer A, option A, is the correct answer of this reaction. So we have solved 5 excellent problems in this episode. We will meet with some other important videos. Thanks a lot. Thanks for watching the video. Thanks very much.